Okay. Yeah, I recorded. Thanks, Jason. Okay. Um, yeah. So, okay. So you can see, we basically can draw the polar plot from the g of j omega, right? So by setting up the formula here, and then you can calculate it point by point by given the value of the omega. Okay, so for example, in this figure, it shows that when the omega runs from 0 to infinity, this one corresponds to omega equal to 0, and this one corresponds to the omega equal to infinity, right? Okay, so yeah, some students ask that, oh, will the polar plot is always semicircle? Apparently it's not. It depends on what kind of transfer function it's going to be. Actually, there is no way to tell you, okay, what is going to be the general shape of the polar plot. Okay, there's no way to characterize the general shape of the polar plot because of the complexity of the transfer function. You could have different kind of a transfer function, right? You could see, for example, you could have a transfer function like this, like s squared plus s plus 1, right? So this is another transfer function. But you follow the same procedure, same definition, then you can always draw the plot, okay? And practically, you can use MATLAB to help you to draw this plot, okay? But you should understand, the plot is obtained by setting up the values of omega and let it go, along a trend. And then you draw it one by one, okay? You draw the point one by one and then connect them. That is your polar plot, right? Okay, so this is always true. It does not change. It's irrelevant of the transfer function. So because of the complexity of the transfer function, you could see many different kind of shape of. There's no way to predict what kind of. Well, actually, there is a way to predict it. And back to 30 years ago, when I was, undergraduate student taking the class, we did not have the MATLAB at that time. Okay, you guys realize that how convenient you guys are. So now you take it as granted. You say, oh yeah, I have the MATLAB. But remember, back to 30 years ago, we did not have the MATLAB software. But we still need to draw this plot. You see what I mean? So the complexity, you can imagine how complicated it's going to be. So at that time, we learned a lot of rules to try to predict what's going on, for the shape. But nowadays, I don't think it's necessary, just because of the convenience of the the MATLAB. Okay, so you have the MATLAB to help you, and so you just get the shape, whatever it is. Okay, but you cannot say this is always semicircle. Okay, the semicircle it's only for this transfer function only. Okay, now so this is one way to draw the polar plot, but did you notice that you see this way you got a semicircle, and this corresponds to the omega to infinity, from 0 to infinity, right? Oh, by the way, okay, once again, let me emphasize it. In this plot, the omega is not explicitly plotted. Did you see it is implied, okay? Implied for each point, okay? But what you plot is actually the real and imaginary, part of the g of j omega, not omega, okay? Even if I draw, the figure shows the numbers of the values of the frequency, but in the plot, the omega value is not explicitly show up. This is different from the Bode plot, right? You see, you remember in the Bode plot, the horizontal axis is always representing the frequency. So the frequency value is explicitly show up. Okay, but but you have to draw two plots for the magnitude and the phase, right? But here we are actually integrated both magnitude and the phase, together in one plot. So the price you pay is that you cannot, explicitly express the value of omega, but you understand it is implied for each point on this plot. That is the feature. That is a very special feature, for the polar plot. You have to remember that. You have to learn. You have to get used to it. Okay, get used to. I mean, this way you actually can find the value of omega if you have the plot. Okay, if you have the point, right? You can actually deduce what is the value of the omega. Okay, based on this formula. Okay, so that's the feature of the polar plot. Okay, but the next I want to show you there is another way actually to draw this polar plot, and actually the other way it's actually more useful for the control guys. Okay, see, if you remember, if you look at here, the semicircle corresponds to the omega to the from 0 to infinity based on this this two formula, right? Okay, but if we look at this function, this is actually the g of j omega. It's obtained by s equal to j omega. So in other words, we actually can think that this semicircle is a mapping. It's a mapping from what? From s to g of s. But this s is not arbitrarily taken. Okay? This s is what? Specifically restrict the s equal to j omega. Right? I mean, you see, if you look at this this formula here, this equation here, this is clearly shows that the g of j omega actually is a mapping. Okay? Mapping from s to g of s. It's a function, complex function. It's just I specifically restrict the s to be what? J omega. Okay? Okay? But you see, this one shows the from 0 to the infinity. Then you might wonder is what about the other value of the omega, right? Apparently, you can see that on the s-plane, we always talk about the s-plane, right? The s-plane actually is a plane that also consists of two parts. This is the real part, which is the sigma. This is the imaginary part, which is the j omega. So imaginary axis of s-plane. This is the s-plane, right? Okay. So we have been talking about this s-plane all the time in the control one. Okay, the real part, the imaginary part. So we know how important this imaginary part is going to be, right? The j omega. But apparently, if I look at this plot as a mapping from s to g of s and restricted s equal to the j omega, and if you look at this half, this corresponds to this part. Does it make sense? You see, the upper part of the j omega axis represents that when omega runs from j0 to the j infinity. Is that right? So you can see I can treat this plot, semicircle, as a mapped value from this part to the semicircle. Through what? Through this equation. Right? Okay. So there's no problem. Okay. Yeah. You can use this one. Then you only deal with the real function. You see, this is our own real function. But if you there's a you can also deal with the complex function, which is here, and that complex function actually is going to be mapped the j omega to this semicircle. So that introduces another way to draw a more complicated polar problem. Why? Because we have not considered the lower part, which represents the minus j infinity to the j0. Okay. Well, you might get an impression that I said many times as omega in physical world, omega always positive. Okay, yes, it is true. For any physical system, the frequency has to be positive. There's no way you get a negative frequency. However, you're going to see that to consider the negative frequency part, mathematically, it will give us a very convenient way to characterize stability in the frequency domain, which is very useful for our control guides. And that is what we call the Nyquist stability criterion. So next, I'm going to talk about everything I'm going to talk about here. It's around the stability, Nyquist stability criterion. Okay, so which is the next one I want to talk about. Okay, now before I talk about the Nyquist stability criterion, any question? Oh, you know what, you check my notes for the control one, because we talk about that in the control. I can't repeat that here, okay? I don't have too much time, to repeat that. This is from the complex function, the manipulation of the complex function, complex number, and the complex, variable. Okay, so you need to go back to check the control one notes and find out that this is from the complex, mathematics. Okay, yeah, okay. So, so before we can talk about this Nyquist stability criterion. We need to introduce the so-called Nyquist contour and the Nyquist plot. Okay, now I'm still sticking with the polar plot. Okay, I did not move away from the polar plot. Okay, this let's make it clear. Okay, the Nyquist contour and the Nyquist plot are still polar plot, but it's a specific polar plot. Okay, specific polar plot. Okay, so I'm not moving away from the the polar plot. Okay, now you see, for example, I still consider this transfer function. Okay, same transfer function, and you already be familiar with this part, right? This is what we just talked about, right? Okay, now I'm going to talk about this part. Okay, you see the whole circle. Okay, how we can obtain this whole circle. Okay, now very straightforward, look of this mapping. You see, like what I said, we're going to treat this g of s as a complex function. So it's going to be mapped from s to the s of s, g of s. Okay, right? Okay, and so this way, you're going to see that apparently this part is mapped to the lower part, right? You see, we already got this down, right? Okay. So it's not surprised to see that the lower part of the minus j omega, frequency part is going to be mapped to the upper semicircle by symmetric, property of the complex function. The complex function is always symmetric with respect to the real axis, right? Okay, so it's a straightforward, conclusion that the lower part is gonna be mapped to the the upper part. Okay, mapped to the upper part, right? Okay, now the question is that okay, the Nyquist plot actual contour, it's a special contour in the S-plane. Okay, the Nyquist contour is defined specifically in the S-plane. It's a special, closed curve. Okay, this closed curve consists of the entire imaginary axis. Okay, we need that, but I want to close the curve. So how am I going to close the curve? Yeah, I'm going to take the semicircle to the right. Why I need this semicircle? You're going to see the reason later. Okay, you're going to see the reason later. Okay, but right now, just take it as mathematically. Just take it as mathematically. Okay, take it as mathematically. Okay, so the semicircle Now, what you see for this semicircle? Yes, of course, this semicircle is going to have a radius, it's going to have a face. But what is going to be the radius? You can see the semicircle starts from what? J infinity to the minus J infinity. You have to use your imaginary scale here, okay? To imagine you have a semicircle as the infinity far away, okay? So what is going to be the value of this radius? Apparently it's infinity, right? Apparently it's infinity, right? If you find that this is hard to imagine, you can assume this semicircle is a what? It's a finite number. So S is going to be equal to the R e to the j theta, e to the j phi, okay? You see, the e to the j phi, you know, this R could be anything, but the phi, the phase, is the same, right? It's the same. It doesn't matter how long this radius is going to be. When you go along this semicircle, the phase phi is going to go from the positive 90 degree to the negative 90 degree, always, right? So the phase that's not related to the radius, okay? When you go along this semicircle. So now you imagine this R is a finite number, and then take this R goes to infinity. How's that? If you find the expression infinity e to the j phi is hard to understand, which I don't think so. I don't think it's hard to imagine, right? So if you really think that it's hard to imagine, you can use this way to try to understand how you get a semicircle with an infinity radius. Clear? Okay. So now you can see that when you go along, this semicircle, and then you're going to see the radius does not change, always infinity, but the phase changes from the positive 90 degree to the negative 90 degree, right? That's exactly what we want, okay? You see, we're going to define, let me erase that, okay? We're going to define this closed curve on the S-plane as Nyquist contour, okay? So from now on, the Nyquist contour is clearly, explicitly defined. It's always this kind of a semicircle in the S-plane, okay? No other, you see, otherwise, there are many, closed curve in the S-plane, right? Okay, many, but we only specifically interested in this special one, okay? Okay, now let's see. If S is gonna taken on this Nyquist contour, now what exactly this G of S is gonna go? Polar plot, right? Polar plot, you see? See? Now, listen to me very clearly, okay? Listen to me. I specify, I do not want S to go arbitrarily on the S-plane. Otherwise, I got confused, okay? It's going to be a long way to figure out this, mapping, okay? But specifically, I restrict S on this semicircle, okay? And then take the value of G of S, mapping, okay? And see how it goes. So, yeah, okay. We got to, since this closed contour, we have a special name called it as Nyquist contour. And you can imagine the plot of G of S should have a special name too, right? Okay, because it's a special one, not an arbitrary one, right? So it's a specifically selected one, okay? Yes. So this polar plot, we call it a Nyquist plot, corresponding to the Nyquist contour. You got my point? Okay, you see, S is going to taken on the Nyquist contour. Then the plot you obtain under the mapping of your transfer function, G of S, is going to be called a Nyquist plot. Okay, so yeah, once this is clear, okay, then we're going to see, okay, how this mapping is conducted, how the plot is going to be. Yeah, well, once you know, after we talk about it here, and it should be quite easy for you to understand. So the upper part is mapped to the lower part here, and the lower part is going to be mapped to the upper part. Well, the question is that where this part is going to map to. Can someone tell me where this semicircle, the entire semicircle, mapped to? Can you tell me? Someone? Can you tell me? Can someone tell me? W equal to 0? What do you mean by the W equal to 0? Well, omega. I guess you're trying to say omega, right? Yeah. Well, you cannot say that is W equal to 0. Okay. Well, you can say it's a 0, but yeah, to say omega equal to 0, it's only partially correct. Actually, this point, that is a two dimension. So you shouldn't mean that is a 0, 0, right? So both real and imaginary part equal to 0 of the G of S. Okay, and this is this origin. Okay, by the way, you have two origin. Okay, one origin is on the S plane. The other origin is on the what? On the G of S plane. Okay, which for the origin on the S plane, which point corresponds to this origin on the S plane? Which point on the G of S plane, this is the G of S plane, corresponds to the origin on the S plane? Not necessarily this point, okay? Not necessary, right? But can you tell me right away? This is very straightforward. Can you tell me which point is gonna correspond to this origin on the S plane under this mapping? Under this mapping? Someone? Quickly, okay? I don't allow you too much time. Infinity 0? Where is infinity 0? Infinity, so let's see. Okay, infinity 0 is going to be infinity and 0. So that's going to be this point. But you see, my plot only goes but not beyond this point, right? So where is the infinity 0 point corresponds to that? Where did you get that? You see what I mean? You see what I mean? So which point should correspond? Which point? Tell me. It is this point, right? Yes, 0.50. Okay, yeah. Very easily to figure out is 0.5. Why is 0.5? Very easy. You see, you take S equal to 0 in, right? This point indicates S equal to 0. If you take S equal to 0 in, G of S is what? G of 0 is what? 1/2. Okay? So it is this point. Okay? It is this point. It is this point that corresponds to the origin. Okay? Okay? I did not draw it. Okay? Okay. So you see, we are now very clear about this imaginary axis. So now I need to figure out where this point is going to map to. Yeah, actually, the entire semicircle is going to be mapped to the origin on the G of S plane under this mapping, okay? Under this mapping, okay? Okay, why is like that? Yeah, very easy to figure out. You see, you have 1 over infinity e to the j phi plus 2 here as the mapping, right? You see, when S, it's let me erase that, make it clear, okay? Okay. Okay, so you can see, okay, then this is a 2. You see, when S is taken on this semicircle, and that's exactly this number, right? You see, that's exactly this number, right? Okay, I'm taking S equal to infinity e to the j phi plus 2. Now with the magnitude is what? Infinity. Okay, you want to compare 2 with a value, complex value with the magnitude is infinity. This guy ignorable. Okay, so if you ignore that, you can see that the mapped value will carry a magnitude is what? It's 1 of infinity, which is 0. So the magnitude is 0. But it does not mean the phase is going to be 0, right? What do you think? Can you imagine how the phase is going to change? You see, apparently, I'm taking this rotation, direction as the clockwise direction. So the phi is going to change from positive 90 degree to the negative 90 degree. You see, it decreasing from positive 90 degree to this point is corresponds to the phi. The phase is equal to 0, and then continue entering to the negative phase part. Okay, the negative phase part until it hit to the negative 90 degree. Okay, so this is in the denominator. So now you can see that when the S is taken on this semicircle, it is actually always mapped to the origin. But this origin is going to have a value of 0 in radius e to the minus j phi. Is that right? You see, because in the denominator, right? So you can imagine, you can express this origin, the mapping process, as 0 multiply e to the minus j phi. In other words, when phi is taken from positive 90 degree to the negative 90 degree on the g of s plane, you're going to see this point is going to stay at the origin, but rotated by the 180 degree from positive 90 degree to negative 90 degree, right? Opposite to that change of the phase in the S plane. Okay, just opposite to the change of the phase change of the change in the S plane. Okay, see, negative 90 degree corresponds to what? Positive 90 degree. Okay, negative 90 degree corresponds to the positive 90 degree. Okay, and so you can imagine the rotation on the G of S plane is also clockwise. Okay, it rotates from the positive 90 degree to the negative 90 degree, right? No, I'm sorry. No, it's wrong. Okay, this is a positive 90 degree. Okay, I'm sorry. The rotation is opposite. Okay, because of the negative sign, right? See, this is from the positive 90 degree round to the negative 90 degree, right? So when the phi is a positive 90 degree on the G of S plane, this point points to the lower, downward, negative 90 degree, right? And then starting from this point, and it start to rotate to the upward, to the positive 90 degree. So the rotation process, rotation direction on the G of S plane is in the opposite direction of the S plane. That is how this semicircle is going to map it to. You can, see this mapping process clearly from this function. Okay, you can conduct an analysis. Okay, so now we can complete the whole mapping. Let me repeat that. Okay, let me repeat that one more time. Okay, so to help you, understand this mapping process. Okay. See, the upper imaginary axis part is going to be mapped to the lower imaginary axis part. It's mapped to the lower semicircle part on the G of S plane. Okay, the upper imaginary axis part in the S plane is going to be mapped to the lower semicircle on the G of S plane. The lower imaginary axis part in the S plane is going to be mapped to the upper semicircle in the G of S plane. Okay, and specifically the origin in the S-plane is going to be mapped to this point, okay? And then when the S is taken on the semicircle, it will always map to the purple color shows. It will always map it to one point that is the origin. But this origin does not stop. Even if the magnitude is 0, its phase keep changing. You see what I mean? Its phase keep changing. Okay? Okay? Its phase keep changing. Okay? That is a very feature. Okay, so now let's go through this process once. Okay, let's say if my S point is go along this direction, go along the Nyquist contour once, clockwise, okay? Now, what you're gonna see is this, is that, you see, from the minus infinity to 0, and then from 0 to J infinity. Okay, we already know that when the omega from 0 to infinity goes this direction. So apparently the whole plot is what? Is that this is going to be the minus infinity too. So it will go this direction, clockwise. Is that right? Is that right? Okay, you see? It goes clockwise. Okay? It goes clockwise. Okay? Okay? So from 0 to the infinity, and then, you see, how this process is going to be completed is from the minus infinity to the 0, minus infinity to the 0, which is this part, and then it keep going from 0 to the infinity, J infinity. So you keep going this way, from 0 to infinity. Okay? Okay? And then this S, after it hit the J infinity, it will enter into the semicircle. See, this point is going to be back to the origin. Okay, yeah. You see, in this time, when S is on the semicircle, the mapped value is going to stay at the origin, but rotate the face until from, you see, from the negative 90 degree, rotate the face all the way to the positive 90 degree. And then start, you see, back to the minus J infinity point again, right? So it will start, the mapping again. Okay? You got my point? Okay? So this is what we defined the Nyquist contour and the Nyquist plot. Okay, it doesn't matter what kind of transfer function it's going to be. Once again, let me repeat what I just said, for this plot, right? I said that you should not take the semicircle as granted, okay? Because we don't know what kind of a shape. Same thing here, okay? See, this is just a special example. You cannot even to say that the upper part is always mapped to the lower part. No, those such kind of a general conclusion, okay? Anything could happen, but what is not changed is what? Is the mapping. So as long as you capture the mapping, okay, you given the transfer function, you capture the mapping, you always evaluate the mapping, then you should be able to get the Nyquist plot. Yeah, of course, the S has to be restricted on the Nyquist contour, right? Okay, so you should be always get to the Nyquist plot anyway, okay, and it is not difficult to understand that the Nyquist plot could be in arbitrary shape, okay, could be in very complicated shape. Depends on what? Depends on what kind of a transfer function is going to be, okay? But the evaluation rule does not change, okay? The evaluation rule does not change. It is always one piece, two piece, three piece. Evaluate this as three piece. And I can tell you that one conclusion we can draw is that if G of S is strictly causal, which means that the transfer function's numerator order is always lower than the order of the denominator. Okay, see, like this one, the order of the numerator is 0. the order of the denominator is 1 because the polynomial, highest power is 1, right? Okay, you see? Okay, see? So if this is the case, you know what? The semicircle is going to be always mapped to the origin. This is you can conclude that, okay? You can conclude that, okay? If the g of x transfer function is strictly proper, okay, which means that the numerator's order is lower than the denominator's order, okay? Okay, see, another example is this. See, this one, the numerator has a power of 1. The denominator has a power of 2, right? Okay, so in this case, if you can evaluate that, okay? You take s equal to infinity j phi into this expression, you're gonna find out that you always get a origin point. But it's just the phase change. It could be more complicated. Okay, so stay at the origin and rotate as much as the phase goes. Okay, as much as the phase goes. But eventually, it's gonna rotate it to the upward. Okay, upward point, right? But the starting, this angle might be different. May not necessarily the 90 degree. Okay, may not necessarily the 90 degree. Okay, it could be other angle. Okay, it could be other. Depends on what kind of expression. Okay, so that's what we call the Nyquist contour and the Nyquist plot. Any question about that? Okay, is it clear? Any question about it? Okay. Okay. Any question about that? No more question? Okay, so I will move on. Okay. So yeah, this page, it just further explain that, how in general, okay, this is a page I just want to show you, like what I said, in general, you don't know which part is going to map to which part. Depends on your evaluation, okay? Depends on your evaluation of the general, transfer function. There is no general rules that you can be told about this mapping process. But in any case, it is going to be the 3-piece, 1-piece, 2-piece, and the 3-piece mapping. Okay, so you evaluate it separately, you're done. And specifically, you should check this point, right? The origin on the S-plane to see where this point is going to map to in the G of S plane. Okay, this is a specific point that you should check, always check. Okay, to verify your mapping is correct or not, right? Your plot is correct or not. Okay, but the nature of the definition of the Nyquist contour and the Nyquist plot does not change. Does not change. Okay, so that is what we call the Nyquist plot. Okay, now if you don't have any more question, I will move on. Okay, I will move on. Okay. Okay. So yeah, now it is the time for us to talk about why I need this specific Nyquist contour to be this kind of a shape. Specifically, why I need this semicircle to be closed and to the infinity, far away. Okay, infinity place. Okay, well, you should understand that when you have the infinity, does it matter it's a square or it's a semicircle? Well, what I want to say is that I want to have a region, have a shape to cover the entire right-half plane. But you are talking about the infinity, so it is really doesn't matter you use a square or you use a semicircle. Okay, you can only compare the difference when the semicircle and the rectangular shape is finite. Okay, with finite value, they make difference. But if you imagine this way, this one goes to infinity, this one goes to infinity, there's no difference between semicircle and the rectangular. Okay, so because of that, That's why we take the easy expression, because the semicircle is still easy to characterize, okay? So we take the advantage of the semicircle, okay? Otherwise, if you want to evaluate a square shape, the conclusion you get is the same, but you have to cut the square shape into 3 pieces to discuss it. No, mathematically, it's going to only increase the analysis complexity, but it does not affect your conclusion. So why you want to find a trouble like that, right? So that is why we want to take the semicircle, okay? Now, another reason that we take the infinity is that, yeah, you know what? I need an entire right-half plane. Why I need an entire right-half plane? Because you see, I want to evaluate the transfer functions of pole and zeros, okay? I want to evaluate, what the pole and zeros of a transfer function is going to map to, okay? See, for example, the first example is that, okay, we're going to take the transfer function as s minus 2, for example, okay? And you understand that this transfer function gives you a 0 in the right-half plane, which is s equal to 2, right? That is the 0 of the transfer function, okay? Then this 0 is also in the right-half plane, okay? So now let's see that if a transfer function has this kind of 0, then what kind of Nyquist plot g of s is going to go, okay? Okay, let's see, evaluate. Well, we go back to the principle of the Nyquist plot. Okay, there's no more than that. Okay, so I'm just doing a specific evaluation here. Okay, it's no more than that. Okay, so you should be able to do it yourself, actually. Okay, okay. So now let me erase that and clearly identify that to show that. Okay. So first thing, what I do is that, okay, to give it a better evaluation, I'm going to write s minus 2 into s plus minus 2 case. Why is like that? Because this way allow me to treat s, it's a vector, 2 minus 2 is a vector 2. So I can, characterize this one as a sum of 2 vectors. So let's see where this s vector and the minus 2 vector is going to be. So you see minus 2 vector, okay? Minus 2 vector, okay? You see, this is the way is that it's here, right? You see? Okay. Plus minus 2. Okay, so it's here. I'm sorry. I did not draw. I should draw the point here. Okay. So this is going to be the minus 2, right? Okay. Okay. See, and s plane. The s vector is what? S vector is on this Nyquist contour, so it's gonna be here, right? Okay. So this is the s vector. This is the minus 2 vector, okay? So now you can see that what is going to be the s minus 2? That is equal to the sum of 2s vector plus the minus 2 vector. Okay, since I have the s vector here, you can imagine, okay, when the point go along this Nyquist contour clockwise, you see this vector is keep shrinking, okay? From the minus j infinity, starting from the minus j infinity, keep shrinking. It goes this way, okay? Until it hits the origin, 0, and then change the direction to the upward, and then keep increasing, okay? Keep increasing, okay? So this is all s vector, right? Okay, so what you need to do is to figure out what is exactly this sum. You see? Okay, that is showing here. Is that right? Okay, you see, s plus minus 2, right? You see, I'm drawing the s plus minus 2 here on the g of s plane. Okay, so on the S plane, you have the S is going along the likewise contour. On the G of S plane and the S minus 2, your plot is going to go this way. Okay, with this part is always equal to S plus minus 2, right? Okay, now when S is on the semicircle, okay, then you're going to have infinity e to the j phi plus minus 2. Does the minus 2 matter? It does not matter. So it's a semicircle. The results, you see, you make this sum, that's going to be just equal to the infinity e to the j phi. That's this semicircle. So what a conclusion you can obtain? Very clearly. When the conclusion is that when S goes through the likewise contour clockwise, so it goes this direction, then S minus 2 is going to encircle the origin of G of S plane. You see, it's going to encircle the origin of the G of S plane, which is this point. You see, once it will encircle this origin once clockwise. Okay, clockwise. So we would like to count how many times this likewise plot is gonna encircle the origin. How many times? In this case, there's only one. In what direction? In the clockwise direction. Same as the likewise contour direction. Okay? Same as the likewise contour direction. So because of this nature, I counted as a positive one. Okay? I specify the clockwise as the positive direction. So if I see the likewise plot encircle the origin once in the clockwise, then I count it as a positive one. Clear? Okay? Clear? Okay? Okay. So now let's move. Next evaluation. What is this? What is this? This is what? This is what? Someone tell me. Someone tell me. What do you mean causal? I mean, what I'm talking about is there's 1 over s minus 2. What this transfer function gives you gives you. Okay? You guys did not listen to me? What are you guys doing? Okay? The first order, what is this? What is this? You gotta answer this question, okay? What do you mean by integrator? Yes, first order, in the denominator, but okay. See what this s minus 2 here give you? Oh my God! What are you guys, doing, for control 1? Okay. Oh. You guys did not pay attention, okay? Honestly, you guys did not pay attention, okay? Okay? Okay, look, the system is not stable. Pole in the right half plane. Yes, that's exactly what I want. You see, this transfer function, I've just specified that s minus 2 is what? Gives you a 0 in the right half plane. Okay, now, here, I write it already in the bracket. This is a pole in the right half plane. So how come you guys, if you guys just look at the notes, the slides, you should be able to tell. What are you guys doing? I can deduce that you guys did not even, listen to my lecture. If you do this, I'm going to stop my lecture, okay? Why should I, talk about the, so much here, and you don't listen to. Did you guys get a point? Okay, so I will need to ask a question time to time. If you follow my lecture, you should be able to answer. Okay, follow my lecture. Okay, follow my lecture. Okay. Well, you see, okay, Iman, I take that's an excuse. Okay. You know what, Iman? Everyone, okay? I, as the professor of this class, I'm not responsible for your internet. Okay? 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 All right? Okay, yeah. So, yeah, you guys need to pay attention, okay? You guys need to pay attention, okay? Okay. So, you can see this transfer function actually give you a what? A pole in the right half plane. Okay, you see, I put these two things in parallel. You see, this is the zeros in the right half plane. Okay, the conclusion is here, right? The conclusion is here. Okay, so now I want to see if I have a pole in the right half plane. So what kind of a encirclement is going to happen? Same evaluation, right? Same evaluation. Okay, same evaluation, right? Okay, what do you think? Why I put a pole and zeros together? Because you see, the pole and zeros, the difference is what? It's the biggest difference is its phase. Because the zeros in the numerator and poles in the denominator. So you don't need me to tell you the detail. You can imagine, okay? If you let S go through this Nyquist contour once, then if you just evaluate the encirclement, okay? Just evaluate the encirclement. It is not a surprise that, if S goes through the Nyquist contour clockwise, then this pole in the right half plane, it's going to encircle the origin of G of S plane once, but this time you're going to have a counterclockwise, right? Why? Because the phase is opposite. One is in the denominator, the other one is in the numerator. So the difference, the essential difference is the phase. Yes, of course, the magnitude could still be different because the magnitude is the inverse of the other one, right? But the magnitude it doesn't affect the encirclement. Okay, it doesn't matter if your encirclement happens this way or this way or this way. What I counted is this encirclement. Okay, encirclement. Okay, your question? Okay, yeah. So okay. So now it is not a surprise to conclude that. If you do have a pole in the right half S plane, okay, do have a pole in the right half S plane, then you're gonna see the Nyquist plot of this right half S plane. Pole, it's gonna encircle the origin of G of S plane once, and it's counterclockwise. So we count it as -1. Okay, we count it as -1. Still counted as one encirclement, but the sign is different. The sign is negative because we specify the clockwise as the positive direction. So now you show a encirclement is in counterclockwise. It's gotta be negative one. You got my point, right? Okay. Well, you see, Jason, that's a good question. For this one, you see, you have S minus 1 and you have 1 over S minus 2. So if you evaluate this guy's phase and this guy's phase, they're in opposite. You got it? Okay? They're in opposite. Okay? Okay? Yeah. So it is very easy. Yeah, exactly. Wally, yeah. Because the inverse, okay? S minus 2 and 1 over S minus 2 is the inverse, right? So you can easily figure out the phase is going to be opposite. So that is why, you have the positive encirclement here, which is clockwise way, and here it's going to be counterclockwise encirclement, and it's counted as minus 1. Any other question? This is the question that I like to hear. Okay, you guys need to ask question. Okay. Okay. Yeah. Okay. Okay. Yeah. So yes, well, you see, like what I said, so you see the definition of the Nyquist, plot and the Nyquist contour is here. You always evaluate the Nyquist plot based on the Nyquist contour, right? This does not change. It does not matter what kind of transfer function you're going to have. This general principle does not change. Applies always. Okay? Applies always. Okay? Yes. Okay, Vali, that's a good question. Okay, you see here when I specify the Nyquist contour, I'm using the clockwise. Well, you gotta pick up one direction as the positive direction. Okay, this is a good question. Okay, I'm glad Vali, you asked this question. Okay, so I can clarify that. Okay, because you see this is a closed contour, so it's gotta be has a direction. But which direction you choose as a positive direction doesn't matter. Okay? Here, I specify the clockwise as the positive direction. Then I will always stick with clockwise. But if you want to stick with the counterclockwise, yeah, you can do it. But then you have to take the counterclockwise as the positive one. Do you see what I mean? So your conclusion is going to be the same. Okay? For example, if you have the right half plane zeros, if you choose the counterclockwise on the Nyquist contour as a positive direction, then you're going to see the encirclement is going to be counterclockwise too, same direction as that one. So you still can count it as 1 because you choose counterclockwise as a positive direction, right? But to avoid, listen to me, okay? Listen to me, okay? Listen to me. To avoid confusion, I will not allow you to choose the positive direction yourself. Instead, I will always specify that clockwise as the positive direction. You got my point? Okay, everyone? Okay. I'm not going to allow you to choose the positive direction, okay, yourself, okay? Instead, I will always, specify that the clockwise, rotation is going to be the positive direction, okay? This is solely because I want to avoid confusion, okay? Otherwise, if you choose, everyone choose different direction, the answer is going to be different, okay? Okay, okay. So now, yeah, so this is the pose in the right half plane evaluation. Okay, now we're going to move to the next one. You see, this is the 0 in the left half S-plane. Okay, you can imagine, you can predict that, right? Because we evaluate the right half plane zeros and the pose. Of course, I have to evaluate, the left half plane, pole and zeros, right? Right? See, you have S minus 2, and that is like you have a left half plane 0, which is minus 2, which is here, right? Okay, but you see, again, you're using the vector addition, arithmetic. So you're gonna have S, and your vector now is actually the positive 2 vector. Okay, positive 2 vector. Okay, okay. And so you can see, okay, when the S is taking on the Nyquist contour, okay, because you see right now your vector becomes a positive 2 vector, which is here. Okay, this is a 2 vector. Okay, and then your S vector is the same, right? Your S vector is going to be the same. So you can imagine if you evaluate S plus 2, it will go this way. What did you see here? What do you see here? Okay? Someone tell me, what do you see here? Come on. What do you see here? Okay? Facing the same direction. So what else? That is not that is not the important point. No encirclement. Yeah, Brian. Okay. You have to have your observability. Okay. You see, you can see in this case what happened. There is no encirclement around the origin, right? No encirclement around the origin on the G of S plane. On the G of S plane, okay? There's no encirclement around the origin. That is a very important observation, okay? That is the case that when you have the zeros in the left half plane, okay? It will always like that. It doesn't matter where this left half plane 0 is going to be located. It doesn't matter if it's a 2, it doesn't matter if it's a 3, or it doesn't matter if it is a 2, minus 2, minus 3, or minus 2 plus j, or minus 2 minus j. It doesn't matter as long as your zeros is in the left half plane. Then you know what? When you evaluate the Nyquist plot of such kind of zeros, you're gonna find out that on the G of S plane, the Nyquist plot will not encircle the origin of G of S plane. Okay, because it does not encircle. So it's not surprising. I'm going to count it as 0. Okay, if you count the number of encirclement, then this should contribute to 0. Okay, okay. Now, before I move to the next page, can you imagine? Can you predict what happens to this? You're probably going to know that the next one I want to talk about is this one, right? So this is going to be the left half plane pose, right? Can you imagine? Can you predict what happened? Someone? Never encircle. Yes, that's right. Yana? Yep, that is true. Okay, that is always true. Okay, so now what I'm going to is, you see the next one is going to be the 1 over S plus 2. Can you predict what is going to be the conclusion? Someone? Someone? Well, yeah. Well, here, let's forget about the stability at this moment, okay? No, I'm not talking about stability here, okay? I'm just talking about the mass, okay? The evaluation of the pose in the left half plane or right half plane, okay? So I'm not touching the stability. We're gonna have a chance to talk about the stability later, okay? After we finish this, we're gonna talk about the stability right away, okay? So at this moment, in your eyes, is only like a 0 pose, in the left or right half plane. Okay, so my question is that, okay, what do you predict that if you have a left half plane pose, what kind of a conclusion you're going to draw similar to this one? Tell me. Okay. Can you please? And this is apparently the way to check if you understand this evaluation or not, right? Okay. Someone? Nobody? Hello? Hello? You know, you guys did not listen to me, okay? You guys did not listen to me, okay? You know, I just, you know, don't. Okay, no, you know, I need someone, you know, to tell me, okay? So you see, this is the right half plane zeros, and now I'm going to evaluate the left half plane zeros. Now I'm going to evaluate the left half plane poles, okay? Same poles. So what kind of conclusion you can draw here? Okay? Same plot, different direction. Yeah, you see, I just wanted the keywords, okay? Keywords is what? You see, you can see from the previous 3 examples, what I'm concerned about is what? It's an encirclement around the origin on the G of S plane, right? It's encirclement around the origin. That is what I'm concerned about, okay? That is what I'm concerned about, right? So in this case, you can imagine that because the phase of S plus 2 is the opposite to the S plus 2, okay? Opposite to the S plus 2, okay? 1 over S plus 2's phase is opposite, just like the right half plane pole and the 0 case, right? We just talked about it, right? This is the same thing here, okay? So if S plus 2 does not encircle the origin, so what? You will not get an encirclement for the 1 over S2 again, right? Okay? So if it does not encircle the origin, I don't care about if it's clockwise or it's counterclockwise. Okay? Okay? So that is the conclusion that we're going to have. So when you have a pose in the left half plane, and then you evaluate that, you're going to find out that the plot is going to go this way. You see, it's going to go this way. Okay? This is exactly what you're going to do, what you're going to see. Okay? So the plot is going to go from the semicircle and then goes the other way. Okay? Go up. So it's a counterclockwise. But like what I said, because there's no encirclement around the origin, I really don't care, what is going to be the direction. Okay? Either way, it's counted as 0. There's no contribution to the encirclement around the origin. Okay? Okay? So this is the evaluation of both left half plane and the right half plane poles and 0. Okay, so let's summarize the conclusion here. Okay, the conclusion we get is this. Okay, if the transfer function has a pole, has a 0 in the right half plane, then the Nyquist plot caused by that 0 will encircle the origin of the G of S plane once clockwise. So if you count the encirclement number, that is going to be the positive 1. Okay? If the transfer function has a pole in the right half plane, then the Nyquist plot, if contributed by this right half plane pole, will encircle the origin of the G of S plane once. But this time, you're going to see counterclockwise encirclement. And the contribution is counted as -1. Okay? Now, for the left half plane, pole and 0 doesn't matter. Doesn't matter is 0 and the poles. The contribution to the encirclement is 0. Okay? The Nyquist plot of this G of S on the G of S plane does not encircle the origin at all. Okay? 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 So that is the conclusion. Okay? Now, yeah, there's some, modification. Okay? Now, the modification is this. You see, we talk about the poles and the zeros in the in the left half plane and right half plane. But we have not talked about the pose right on the imaginary axis, right? You see, this could be possible, right? For example, if you have a transfer function, this is the integrator, 1 of s. 1 of s has a pose at the origin, okay? And with a 1 over s squared plus j omega squared, and this one give you the pose at the positive minus j omega, right? So it's gonna be either here and both here and here, right? 2 poles. And this pose is on the, all of this pose is what? It's on the imaginary axis. Imaginary axis, right? Imaginary axis. Okay. So what about if this is going to be the case? No, we cannot avoid this case in the transfer function, right? Yeah. Okay. So in this case, you have to modify the Nyquist contour a little bit. You cannot use the original one. If you use the original one here, so when the s hit this pose, you got trouble because this g of s is what goes to infinity. Irregular, not regular, right? So the evaluation actually it's done by slightly modify the Nyquist contour. Okay, you see, in this picture it shows clearly, and you're gonna choose the Nyquist contour. You see, go here, and then use a very small indent, small semicircle indented to the right around this pose, wherever this pose is located. You can always do that, right? Okay, and then continue, when you hit another pole on the imaginary axis, you do this small indent again, and this indent has to be to the right. Okay, and you finish every pole with this small indent, and then this will be a modified Nyquist contour. Okay, this will be modified Nyquist contour. In other words, right now you're going to evaluate Nyquist plot based on this closed curve instead of this one. Okay, this is just solely try to evaluate to avoid the irregularity, non-singular. You see here, when you hit the pole, the transfer function is not singular. Okay, it goes to infinity, right? So we just try to avoid that. So you modify the Nyquist, contour this way, not this way, not this way. Why? Because you see, if we go to the small indent, to the right, then we basically treat this pose on the imaginary axis as a stable one. Actually, it is stable. Okay, it is stable. It's oscillation, but it's bounded oscillation, so it is a stable one. Essentially, it's a stable one. Okay, if you use this modified contour, you're going to treat this pose as well. It's in the right half plane, so that is going to be the unstable one. You're going to distort the picture. Okay, remember, where this pose located, it does matter because it will contribute to the encirclement or not, right? So if you use this Nyquist contour, then you will not see the contribution from the pose on the imaginary axis to the encirclement. Okay? Now, if you use this one, then what? Then this pose is going to contribute to the encirclement, which distorts the picture, okay? Which distorts the picture, right? Okay? So that is why this is not what we want, the indent direction. Instead, we're going to always like to use this small semicircle indent to the right to construct the modified Nyquist contour, and then we conduct the evaluation of the Nyquist plot. Okay, so this is the singular case. Okay, other than that, there's no other case. Okay, you need to consider, because you basically run through all the possibility. Okay, you basically run through all the possibility. Okay, so I think I will just stop here, take some questions before I move to the general evaluation. Okay, then we're going to talk about the Nyquist stability criteria. We're ready to talk about that now. Okay, so any questions? Okay, no problem, Tara. Okay, as long as you guys pay attention to the lecture. Okay. Why you have the time, here when I talk, and this is so good time for the interaction. Why you count on the recording, right? You said, oh yeah, the lecture is recorded. So I can always go there to listen to the tape, but you missed this time, right? Okay. Yeah, the assignment is it's specified in a schedule file. Okay, I think it's midnight of tomorrow or Wednesday. I cannot remember. You can check that from the schedule file. Okay, it says very clearly. Okay. And so what is it? Well, encirclement, yeah. Okay, Danilo, yeah, that's a good question. You see, that's exactly what we're going to talk about here. The encirclement is going to affect the stability. We can actually deduce the encirclement from deduce the stability of the closed loop system from the encirclement. Okay, we're going to talk about that. Okay, when we talk about the stability of this closed loop transfer function, this closed loop system, you see, this is what we're concerned about, right? So when we talk about the stability of this guy, then you're gonna see how the encirclement is gonna, help us deduce the stability information. Okay, but at this moment today, you gotta have a solid understanding of how this evaluation of the likewise, plot is gonna be done. Okay, for the pole zeros, evaluation. Okay. The left plane or right plane, pole zero evaluation, you gotta have a solid understanding of this, procedure. Okay. So you see, in the on Wednesday's class, when we move to the general system, when we talk about the closed loop system stability, by using this knowledge, you should not say, wait a minute, this seems new to me. That doesn't make any sense. I'm not going to repeat this. Go back to repeat this on Wednesday. Okay. And you can understand that. If I repeat that, always repeat it, and we cannot move. Okay. Yeah. Well, you see, first you just need to evaluate, near. Okay. You see, you first need to evaluate if there is an encirclement or not, right? Okay. You read my notes. Okay. Read the procedure. Okay. I've just talked about. Okay. And if the encirclement is clockwise way, it is counted as a positive one. If the encirclement is counterclockwise, it is counted as a negative one. If there's no encirclement, then you count it as 0. Okay? Because once again, here I said it is very clear. We specify the clockwise as the positive direction. Okay? So we're not going to have the confusion set up. It's always clockwise as the positive direction, which means that on the likewise the contour, likewise the contour, always this direction is positive. Okay, always this direction is positive. And then when you evaluate the encirclement on the G of S plane around the origin, you should also look at this way. If it is this way or if it is this way, right? Okay, so if it is clockwise, positive 1. Counterclockwise, negative 1. No encirclement, you see, like this one is no encirclement, 0. Okay? Any other question? Any other question? Hello? Any other question? No more question? Okay. All right. So if you don't have any more question, then today's lecture is going to be stopped here. Okay.